Okay, first, the list of spaces. Second, are these spaces heated or not heated? Depends. So usually storage, kitchen, restrooms, they don't have heating system. And then divide the building into spaces with the same size and the same use. Okay, so when there is an exhibition in the art gallery, probably the rest of the building is empty because everybody is meeting on the art gallery. But when there is nothing on the art gallery, people are either in this meeting room or the director office will be in the office. People will be working on the workshop. Okay, so we have to understand what the building is about, and nobody is going to tell us this. In this building, in the TDS building, we have offices there, and we have classrooms. But in these classrooms, they are different. We have the chemistry labs there. We have the big studio there. We have workshops. Okay, so understanding this building, it's even more difficult. And probably we need something special for the wood workshop, because the activity that people are doing there doesn't have anything to do with the computer lab. Okay, so we have to understand this. Okay, so we need a system for the wood workshop because we have a lot of particles, and we need probably there ventilation is more important than here. But in all the classrooms, we can assume that we have the same occupancy, we have the same schedule. For the big studio, maybe we would do something different, because if that big studio is full of people, the requirements would be different. For the chemistry labs, probably are there any health issues in that or hazards in these chemistry labs? We don't know. We will have to find out. Okay, but when we have complicated buildings, probably we need different systems for different spaces. In this building, I think we can assume that the rest of the spaces are the same size and they have almost the same use, like offices or meeting rooms or whatever. But the gallery and the lobby are two different things. Okay? So I need this, and in the gallery and the lobby, then we have a schedule. And that schedule is from 0. Zero, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 23. Okay, so we have 24 hours. Well, we can start with 1 and we finish with 24, or we start with 0 and the last one is 23. Okay, but we have 24 hours. And now we have to figure out how many people we have in the lobby, in the gallery, or in the rest of the spaces according to that schedule. Well, this is easy because from midnight to what time does it open? I was there at 8 and it was locked. So let's assume that it opens at 9. Okay, so at 9 we have this. So the lobby, the rest of the spaces in the gallery, from midnight to 9 a.m. it's locked. And now I have to type the number of people that we have in each space at different hours. So what is the art gallery about? Well, I tell you, if you go to the art gallery right now, it's empty. There's nobody there. 0 people. Maybe one, the one that it's the person that it's opening the building, and that person has to be there for, I don't know, until the building is locked again. And nobody is aware that there's an art gallery on campus, so it's too bad. But sometimes they have events. So I made an assumption for the other section, and I'm going to assume something different. So imagine that the art gallery, the art gallery space, they have events every morning. So because they have a class for all the art students, they go there to see the exhibition and to work in the art gallery, because this can be like a workshop or whatever. So imagine that from 9 a.m. to 12 to noon, they have activities there, and the art gallery is full of people. Okay, so let's do this. And then what's the occupancy of art galleries? So we need a reliable source in terms of occupancy. So what is the most reliable source in terms of occupancy? It's the ASHRAE. Okay, so the ASHRAE is the American Society of Transport, American Society of Heating, Refrigerating, and Air Conditioning Engineers. Okay, so they are engineers, they are not architects, good. And they are related to heating, cooling, and air conditioning. So everything that has to do with heating, cooling, and ventilation, it comes from the ASHRAE. So it's in the United States. This is everything. So if you need an official data, it's in the ASHRAE. So there are like hundreds of books with hundreds of pages each. Do you have to know all the ASHRAE by heart? No, we don't. But at some point in our lives as architects, we will have to go over the ASHRAE and to find out the information that we need. We should have done it, but well, we didn't use the ASHRAE as a text, as a required text, because it's tough dealing with the ASHRAE. But if we, for example, ask for occupancy of spaces in ASHRAE, functional spaces of public buildings. Let's try to find out, and we have a PDF. That's scary, because the ASHRAE PDFs are like this. Okay, this is not ASHRAE. I need a table. Oh, look at this. Predicted versus actual occupancy of Manchester Art Gallery. November, UK, Manchester, UK. Okay. So what's this? So this is standard ASHRAE maximum occupancy, people per square meter, used in Design Builder. Design Builder is a simulation software. And this is the actual maximum occupancy in the art gallery. Okay, so we need a figure to simulate things, and then we need actual maximum occupancy in this art gallery. Okay, so here we have the circulation, we have the gallery, we have the exhibitions, and we have the entrance. Then we have the eating and drinking area, the reception, and the shop. So this is what ASHRAE says, and this is the actual, okay? Because sometimes we simulate something when we are designing, but the real building has a different occupancy. Let's use this, okay? So if we have display and public areas, public circulation, galleries and exhibition, so this can be the gallery and the lobby, because it's a public circulation, and they suggest 1.15 people per square meter. Okay, so they suggest that the occupancy in the art gallery in the lobby it's 0.15, 0.15, it's 0.149, okay, 0.15 person or people per square meter. So 1 square meter is around 10 square feet. So here we have 0.15 person, people per 10 square feet. Okay. So if we multiply this times 10, okay, no, if we do this by 100, we have 15 people times or by 1,000 square feet. Okay. So that's it. We have 15 people per 1,000 square feet. So now the question is, how many square feet we have in this art gallery? So we open the Revit file, and on the Revit file, we can work with spaces or we can work with rooms. In architecture, you can insert room. So if you insert that room, here we have information about the volume and the area. So for the area, you see that we have 4,000 square feet. Okay, 4,034. If we have 15 people per 1,000, if we multiply this times, so how many people? If we have 15 in 1,000, we have 60 in 4,000 square feet. Does it make sense? But according to this ASHRAE document, what's the actual occupancy? Well, it's even less, so we will use that. But we can have other sources of information. For example, if I remove this room and I work with spaces, I can type here analyze, and then I can select spaces. Okay, so that space, if I select it, I have the area should be the same. Okay, the area is 4,034 square feet, so the area is the same. But here I have information about the building. Okay, so here you see we have space type, and if I click here building, I have all these lists with a lot of elements or a lot of uses. I found before this exhibit space. If you click on exhibit space, here you have what they suggest for this exhibit space. They suggest 21 square feet per person. Okay, so that's a different data. So we had this in terms of a person per square meters, but now we have a different option, which is 21 square feet per person. Okay, if we have 21 square feet per person, how many square feet do we have? We have 4,000 square feet. So how many people would we have here? 200. 200 times 20, it's around 4,000. Yeah. So according to this, we can have up to 200 people. Okay, so what do we do? According to ASHRAE, I have 60 people. According to Revit, I can have up to 200 people. So that's life. You have to make a decision. If you maximize, I told you that we always tend to be on the safe side. Okay, so I prepare my calculations, my building for the worst case scenario. And then if it's better, okay, that's fine. What is better in terms of energy, 200 or 60? 60, because the more people, the less energy I need. Okay, so if 200 is worse, I'll use 200. But I'll talk to my client. Okay, so, okay, do you think we can have 200 people in this art gallery. Yes, when there's an exhibition, we can have up to 200 people. But this is how it works. I try to find the numbers, and then if I find two different numbers that are completely different, 260, they are completely different. So it's then I have to figure out what to do. But nobody's telling us. People will complain if something goes wrong. Okay, but nobody will tell us, oh, use 200. No, use an average, something between 260. I'm going to use 200 now, but because I want to be on the worst case scenario. So I'm going to assume now that after the opening, well, not at 9 a.m. At 9 a.m. I can have in the gallery, I can have like, let's say 20 people preparing the exhibition or whatever. And then I have 200 for 3 hours. And then I have fewer people, and in the afternoon, I assume that the building is, or the art gallery is not operating, so I have 0. Okay. But why have I done this? I have made that assumption, and probably I have talked to the client. So what do you think? What do you expect? Or do you want to open the gallery again for visiting the exhibition in the afternoon? Yes. So how many people do you expect? Let's say 50 people for 3 hours. Okay, but there is not a straightforward answer to this. We have to make assumptions, and okay, if our client considers that this is this is something that they predict, okay, so we can use this. What about the lobby? So the lobby is locked, and then at the beginning we can have like 5 people in the lobby preparing things, and when we have the exhibition, how many people in the lobby? According to this ASHRAE, this is for galleries, exhibitions, and public circulation areas. Okay, we're going to use this number. I use a different number for the gallery, but for the lobby, I'm going to use this 0.15 people per square meter, which is 15 people per 1,000 square feet in the lobby. Okay, and now what's the area of the lobby? I have to create another space or another room. Space here. And then if I select that space, the lobby is, the area is 1,035 square feet. Okay, so if my occupancy is 15 per 1,000, so I can say that here we have 20 people. Why? Okay, it could be 15, but I'm going to use 20. Okay, so now what's the schedule of the lobby? So I assume that when we have the exhibition, we have 20, 20, 20. Then after the exhibition, people stay in the lobby, and then in the afternoon, I have only 5 people, and then 0. Okay, so that's the schedule of the lobby. What about the rest of the spaces? Well, if I have an exhibition there, I don't have people on the rest of the spaces, so I can assume that I have 0. And then in the afternoon, we can have in the meeting room, I think there are like 5 or 6, no, there's 15 seats here. And then, okay, I'm going to, so in the meeting room, I think there were like 15 people. In the kitchen, nobody. The office, we can have 4. In the director's office, 2 maximum. The workroom, we can have not 4 because those are small spaces. For the receiving, I can have 5, and the workshop maybe 4, and that's it. So in total, I have 15, 19, 21, 21, 5, 30, around 34 people. So if I assume that everybody is working on those spaces, let's say 34, and then 20, 20, and 0. Okay, but this is my assumption based on what? Based on common sense, based on what my client expects for the art gallery. But we had, well, that's impossible. We don't have full occupancy always. Okay, so that's why we need to deal with that schedule, because we don't have 200 people in the art gallery, 50 people in the lobby, and 34 people in the rest of the spaces 24 hours a day. We don't have that. So that's why we have to prepare that, that schedule. Okay, and now we have the total people. So for the total people, I add up some of people in the lobby, people, people in the gallery, the lobby, and the rest of the spaces. And then I click OK. What? Yeah. And now I drag this down. And this is the, okay, so every time I have a sum of all the people that I have in all the spaces. Okay, what can I do now? I can use the Excel file that I'm using here. Okay, so this is my Excel file, and I have to change first the number of people. So when I come up with the number of people that I have here, I copy all these and I paste it on this column with the number of people. And what's that? Why do I have 122 whatever? Because I have copied a formula from other Excel file. So if I just want the values, I have to type here just values. And now I have here 0, 25, 220. Okay. So if I want to copy something from a different Excel file, when you paste, make sure that you paste values. You don't paste the formula. So this is the number of people. And then the total CFM. What we did before, the total CFM was 20 CFM per person. So that was each value here was the value here, the number of people, times 20. This morning, I have found out other requirements for right? Okay. So here, depending on the space, we have requirements for CFM per person. We have CFM per person, and then between the parentheses, we have the liters per second per person. Okay, so these are international units. These are the CFM we're using. So we can have 5, 6, 9, 11, 13, 15, 16, 17, 26 in health club weight room. Okay, so we don't have this in an art gallery. And we took 20 by default. Okay, so 20, it's very conservative. We are always thinking of about the worst case scenario. So if you want to be more precise, you can find a table from the ASHRAE, always from ASHRAE, with the default CFM per person. And then if the classroom is 13 or 15, it's not 20, okay, that's fine. If you want to do it faster, you can use 20 here. And this is what we did on the first assignment, using 20. Keep in mind that these values that we find in the ASHRAE are always the minimum values. Okay, so if I find here 17, that means that the minimum is 17. 20 is totally fine. So I can lower this number, but I can go up. I will spend more energy, but then if I have a good equipment and that equipment has the variable air volume, and we have sensors, and we're not just supplying energy for 20 people, but we can adapt the system to the real occupancy, that will be great. Okay, but here I'm going to use 20. In the other section, I used different numbers, and I adapted the CFM to the spaces. But here, by default, I'm using 20. So here we have the total BTU hours, okay? Because with this we have the total CFM, and here we have the calculations. No, this is pounds per hour from CFM. We have the pounds per hour, and here we have the total ventilation load. And here we have the energy, and here I add up this energy. So that's it. Okay, so that's what I have done here. Is it correct, or shall I do anything else with it? Heat recovery. Heat recovery. Yeah, but before dealing with heat recovery, do you have to change anything here in these columns? The indoor temperature, do you have to change the indoor temperature? Okay, for the storage. We don't have storage here. When I have no occupancy, I have no heating loads. Okay, so that means that I'm not keeping 70 Fahrenheit even when the building is empty, because I multiply by the number of people. So I can keep comfort temperature. So comfort temperature is 70. So I can keep this column. The relative humidity, a comfort relative humidity. If we're in an art gallery, people is almost as important as the works of art. So I don't know what the best relative humidity, indoor relative humidity for. Probably it has to change. If we are displaying paintings, it's different than if we are displaying marble sculptures. Okay, so the relative humidity should be different. But anyway, 50 is comfort. But what about the outdoor temperature? Where does this outdoor temperature come from? The weather underground. But I have found something better. Okay? So for the weather underground, remember that we cannot copy and paste the values. So I have found the PV watts. Okay. So if we go to the first page for PV watts, now we are in Keene, New Hampshire. We are not in Manchester or whatever. We are in Keene. And there you go. Now if we go to the system, forget about all that, because this is to calculate the PV array. We're not doing that. I want just outdoor conditions. So if I go to the results page, I find this monthly or hourly data. So select hourly and open. Okay. So here we have location in New Hampshire, the location, all that stuff. And here we have the month, day, hour. Okay, so we can select the daily or the hourly information here. So month 1, January, day 1, first, hour 0. So from 0 to 23. From 0 to 23. This is January the 1st. And that will be January the 2nd. Okay. So I can assume that the coldest day is going to be on January. But when in January? So I can, with this, I have a powerful tool and I can predict what the coldest day is. How can I do that? Well, here you see that we have a lot of information. The beam, this is to calculate the solar energy, the beam irradiance, use irradiance. But I need this, I need the ambient temperature. So this is the outdoor temperature here, but it's in Celsius. So the first thing I have to do is to convert this from Celsius to Fahrenheit. So what's the formula to convert Celsius to Fahrenheit? I think it was somewhere. Celsius to Fahrenheit formula. It's quite easy. It's where's the formula? This one. Okay. So it's Celsius times 9 divided by 5 plus 32. I'm going to copy this and I'm going to paste it here. So that cell equals this. So now I have to replace this number by the temperature in Celsius. Click OK. So -2, it's 28.4 Fahrenheit. Then I go all the way down. Here. Yes. And this is the the hourly temperature in Fahrenheit. Now I want to select the coldest temperature for winter, the hottest temperature for summer. How can I do that? I can use another function in Excel. If you click here, function, you have maximum and minimum. Okay, we have this at the beginning because I have used those functions before. If you don't find them, you can type here minimum. Click, and min, it's the minimum value of a series of values. So I have to select minimum. Well, I found out something here. Okay. This doesn't work when we have a formula in this. Okay, because I want to select the minimum value of all these values. So what I'm going to do is to select this column, Control-C, I paste it, and again, I'm going to paste it as values. Okay, so now we don't have a formula. If I type here, this is 28. It's not, if I type here, we have this. So when we have a formula, something doesn't work. So I want to find here the minimum. So I'm going to type this, minimum, and it has to be the minimum of all these here. Okay, so the minimum value is a -11 Fahrenheit. So according to this, the minimum value that we can have throughout the year in Keene, New Hampshire is -11 Fahrenheit. Makes sense. But now, when does it happen? Okay, so I select this column and I have to find negative 11.2. If I find next, this is it. Okay, so on this day, which is January the 3rd at 6 a.m. Apparently, this is the coldest temperature in January. So what I'm going to do is to select that day. Okay, so it starts on January the 3rd, starts here, and it ends there. Okay, so this is January the 3rd. Okay, so this probably it's the coldest day in January. Okay, so I'm going to copy this, and now I can paste it here. Remember that I couldn't do that with the weather underground, but now I can copy and paste. And I'm going to paste only numbers. So this is the coldest day. So that's the coldest day. Do I have to do anything else? Not really. So where do I consume the most energy? At this point, when I have the highest occupancy, when I have 220. Okay, so this is value 0.11 to 0.1. But anyway, this is the highest value, and this is because I have two peaks. This happens at 11 a.m. because at 11, no, it was 11 here. At 11, I have 220 people. Here, this is the peak value, 449,000. And then there is another peak value here. Yes, in this 180,000, I have another peak value here. Okay, because I have more people in the morning than in the afternoon. But this is like a break or whatever, and then we have we open the building again, and we have this. Okay, so if you download this from PV Watts, we have to find. But again, it's very easy to understand where or when the maximum value or the minimum value happens. If I want to find the maximum, I have to go to this. I can copy this column again here, and then I can change the function. So if this is the minimum, if you just type here max, now we calculate the maximum, which is 89. Now, on what day do we have 89? Select, find. We type here 89, find next. So that day is the maximum temperature, and that happens on August the 31st. Okay, so in summer, I should select that day, August the 31st, because it's the hottest day, summer. Okay, again, we have to do this for a day in winter, and then we have to do this for a different day in summer. Okay, we have this table. Now we need a heat recovery. Okay, so for that heat recovery, we can type the value here. What is that value? 60, 65, something like that, okay? And then the heat recovery will be working throughout the day. What's the, here? What's next column? It's the energy in BTUs, but with heat recovery. Okay, so that's the energy with heat recovery in BTUs. What's the formula here? That was equals the energy without the heat recovery times 1 minus the heat recovery efficiency divided by 100. And now if I drag it down, there you go. Let me change the format. Okay. So if I have 430,000 with the heat recovery, it's only 150,000. So if the heat recovery is 65, I consume only 35%. Okay, so that's the idea. So with the heat recovery, we can have huge savings. So in this kind of buildings with a high occupancy, in a single family house with 2 or 3 people, it doesn't matter. But when we have hundreds of people, the heat recovery matters a lot. Okay, so this is mandatory, having heat recoveries when we have this kind of buildings. Okay, so this is the energy with heat recovery in BTUs. Unfortunately, when we are calculating electricity, we don't use BTUs. We can use BTUs for, if we are dealing with the boiler, we can use BTUs. And what is the size of my boiler? It has to be the highest value of this. So if I know this function, I can use max of this column. So this is the maximum value, 157,000 BTUs. So if I'm going to buy or I'm going to recommend a boiler, now I have this value as a reference, and then I can go here to see boilers in BTU. Okay, so boiler capacities I need. Okay, so this boiler. So here we have information about natural gas boilers, and they range from 239 to 318. Okay, so this is more than enough because our boiler has to be 157. Okay, so we need something that is above this number. So we have to go to a catalog. So 318 it's too much, probably this 239. If our boiler is 150 something, so this is more than enough. Okay, here we have another, this is 100 to 132. 132 is not enough. Okay, so we need this one. So we need to find a boiler that is above our number, and it's not too far away from our number. Yeah, so if we have 157, something between 180 and 200, it will work. Okay. If we have something that it's too powerful, we can have a problem. Because if this is the power that we need, and this is time, okay, if we request 150,000 BTUs, and we have a boiler with 140,000 BTUs, what happens? If we start running the boiler, we heat up this but we don't get this power because the boiler is 140,000. So we will never get to this value. So that's what this is what happens with the boiler, that it's below our needs. What if we have a boiler with 500,000 BTU? So we have a boiler that is far. If we need 150, and we have something like that, the boiler will start, and we will reach this power immediately, and then the boiler stops, and then we have to start and stop again, start and stop again. So that's good, but this is not good for the boiler. Okay, so what do we need? If this is the requirement, if we have a boiler with let's say 200 BTU, it can happen something like that. It will have some time to request this, and then like this, and then like this, and then like that. Okay, so here the boiler turns on and off every 5 minutes. This is bad for the boiler. If this is 2 hours, it's okay. So this is what happens with the boiler, that it's not enough. Our clients will get cold there because we can never get the power that we need. And what happens when we have a huge boiler, much bigger than what we need? If we have this cycle, and that is harmful. So that damages the boiler. So we need something that is above the requirements, but not too much, so that this cycle is repeated every 2 hours instead of every 5 minutes. Again, common sense. And we're not going to decide that, okay? So we have to explain what we want to the provider of mechanical equipment. And okay, so we need this. I have this space, I have that schedule. This is the occupancy that I expect. So what do you recommend? Okay, so so your maximum power is this, so I recommend you that. So it's always okay, so we don't have to decide. We know that we need something that it's above 150K BTUs. But depending on the schedule, depending on the space that we are designing, someone has to recommend the boiler or the element that we need. Okay. Anyway, we know that it has to be above 157,000 BTUs. So that's all we need so far. But this is for thermal energy. So this is thermal. I told you that there's another coefficient, which is the COP, the coefficient of performance. So the coefficient of performance, if we need this, if we want to turn this energy with heat recovery from BTU to kilowatt hour. I'm going to do it the other way around. I'm going to paste it here, and then the COP. Okay. So first, if I'm dealing with fuel, I can work with BTUs. But if I'm dealing with electricity, I have to convert BTUs into kilowatt hours. So how can we convert that? There is a converter. BTU to kilowatt. Okay, so we have this number 0.000293. There, I copy this number, and this column equals the value in BTUs times the value in kilowatt hours. Then I write it down. Again, copy the format. And this is it. Okay, so in this case, what is the maximum power? If I'm dealing with fuel, this is the power that I need. If I'm dealing with kilowatt hours, this would be the maximum power. That we have good news, is that electricity works for us. Okay, so the COP means that the actual energy this is the thermal energy in kilowatt hours, but the actual electric energy is the thermal energy divided by the COP. So I think I explained that before. COP, and again, this is the most important concept that we have to understand in this course. COP, it's always thermal divided by electricity. Okay, so if I have the thermal, I have the COP, the electric power in kilowatts or kilowatt hours is the thermal in kilowatt hours divided by the coefficient of performance. Okay, so that's very, very interesting. And then there are other codes. We have the EE, the R, we have the seasonal energy efficiency ratio. So there are different things because we have different units. There are ratios between BTUs and kilowatt hours between, but I like the COP because we have kilowatt hours in kilowatt hours. So I can understand that. I don't convert units again. So that's why I turn everything to kilowatt hours, and then I do this with the COP. What's the COP of commercial heat pumps? So last time I selected Daikin. Reliable people, German, Deutsch. And here, do I have I need like a catalog. Okay, this girl, and okay. So here we have information about the COP here. This is 4.56, and these are other ratios. And again, if we convert things, so all these numbers are related. If we are working in international units, kilowatts or kilowatt hours, we select this. The higher, the better. I told you that 2 is quite bad. 6, it's incredibly good. 4.5, it's good enough. That depends on the outdoor and indoor conditions. Okay, so again, we have an idea, it's around 4.5. Okay, but we have to deal with the provider because it's not the same. We can't use the same machine in Keene or in Miami Beach because the COP, it depends on the outdoor conditions. So probably there are machines that are prepared for warm countries. There are machines that are prepared for cold countries. But if we have this information, we can type here 4.5. All the way down. And now this is electricity equals electricity divided by COP. And we go down. Okay. And now we have to select the maximum. So I'm going to copy this here. And this is the maximum in electricity. It's not thermal. So the maximum value in electricity, it's 10.25 kilowatts. So if I'm looking for a heat pump, I would need I would need the catalog. I think I had the catalog. No. Let's open the Daikin. Okay, here we have BTUs, but I want the power in kilowatts. Okay, so this is 24 kilowatts. This is do we have information? So this is 24. This is 5,000 watts, so it's 5 kilowatts. This is 3.5. It's not enough. 64. Okay, anyway, we have to find something that is above 10 kilowatts, because this is the maximum electric power that we need. Do we need one phase or three phases? There's 50%. So what do you think? One or three? Three. Good. Three. One is less than 5,000 watts or 5 kilowatts. We need one phase. More than 10 kilowatts. We need three phases. Okay, so we need just a circuit. If we're talking about electricity, we need a circuit, a three-phase circuit, only for the heat pump. It makes sense. Okay, so that's when we have an electric system, we need just a circuit, a three-phase circuit for that electric circuit. But now we have options. If we want a boiler, I have to see the BTU hours, and this I have to request this boiler. If I'm running the building with electricity, then I need that electric power, and we need just an electric circuit only for that device. So what's the goal of this? Well, probably because this is too big, we can split this into the energy with heat recovery. So you can paste this on the PowerPoint. Okay. And we can copy and paste this one for electricity. Okay, so here I have information about the occupancy, the temperatures, all that stuff, number of people, the schedule, and the energy with and without the heat recovery in BTUs. Okay, and this is the energy with heat recovery with this machine, with this COP, and this is the electrical energy, and this is the maximum. We should type here the units. This is kilowatt. Yep. And then we need the graphic. Oh, the graphic, sorry, this is just the energy without the heat recovery. I think we're going to need the information with heat recoveries. If I want to change that, is the column M, and it has to be O. So it's M, O, and O. Okay. So now this value is with this. And we can't paste in the same graphic kilowatt hours and BTUs. Okay, so if this is BTU, we might need a graphic for BTUs. And then if we want the kilowatt hours, copy and paste it here. And if we want this to be kilowatt hours, we have to drag what now has really R column. Okay, so here we have values. You look at this. Here it ranges from 0 to 180,000 because these are BTUs. But now I have to change this to kilowatt hours. Okay. The graphic is the same, but the values are completely different. So if we are dealing with heating fuel, we need the information in BTUs. If we are dealing with heating in electricity, we need this information in kilowatt hours. Okay, so we can paste this for the kilowatt hour, the electricity. That's the electric heat pump for heating. And then we can have this value here. And this is the fuel, the gas boiler for heating. And probably we need a table like this so I can paste the information about the heating. In BTUs. And now I can paste this graphic. Okay. So that's when if I decide on a heating system with a gas boiler, I need this column. If I have the same, but with the heat pump, I need this column. The graphics look the same, but the units are different. Those are BTUs, and those are kilowatts. Okay. For cooling, we don't have the option of BTUs or electricity. for cooling, we always need a heat pump with electricity. Okay? So if you do this for cooling, what do we have to do? We have to select the warmest day, that it was August the 31st. You have to save this as, if this is winter, you have to save it as summer. You need another Excel file. You have to change the outdoor temperatures. Okay. And then if we change the outdoor temperatures, all these numbers will change accordingly. So where is in PV watts, we have this day, August the 31st. We need these values up to this day. Then Control C. Here Control V. And now everything changes. Well, and now everything is negative. So when we are doing this, it shouldn't be the maximum, that should be the minimum. When we are dealing with negative numbers, this has to be minimum. And minimum. But the thermal doesn't make any sense in BTUs because when we are dealing with heating, everything has to be in electricity in kilowatt hours. So for the summer, I need this in kilowatt hours. And this is the electric heat pump for okay. So here we have the whoop. Oh, I see. You see, I have changed the numbers, and now when you paste the graphic, that's interesting. Okay, so it's still related to the Excel file. If I undo, I undo this. No. But if I undo what I did in the Excel file, now that changes. Anyway, you know what I did. So probably, okay, so now everything changes. Even in the, how can I, if I don't want it to change, probably if you copy this and you copy this like an image, now it doesn't change. Okay, but if you copy this as a, here you see that we can work. Okay, that's cool. Sometimes I might need that it's still related, so I can still control this for the PowerPoint, but sometimes I don't want that. Anyway, so be careful. If you do this with two different Excel files, it will work. But if you do this with the same Excel file and you change the values, then the graphic will change. Be careful. Okay, so we are done with everything that is related to the calculations. We started defining, but everything starts here. Okay, so this is my building, and I need to come up with occupancy. I need to decide what spaces are heated or what spaces are not heated. And then I have to come up with my own schedule, and I have to deal with the number of people that I have in different spaces at different times of the day. And then I can use this and have the energy. But now I have to work with the system itself. Okay? because this is Excel file. Where is the, now you have to work with Revit. And so we have to come up with an idea. I think in this building, the art gallery can be divided into two different spaces. So if this is divided into two different spaces, I can have supply diffusers here and return diffusers there. Because if I close this partition, in one of the spaces I will have supply, and the other I will have return, and it won't work. So in the event that we can divide this, I need supply and return in this, and I need supply and return in that one. Okay. So what can I do? If you go there, you will see how. Well, I'm going to divide this. Okay. So if you go there, there's a line of diffusers here. There's a different line of diffusers there. And then in that, there's another line here, another line there. There's a false ceiling. We don't see the exposed ducts. We only see diffusers. Okay. I don't know how many diffusers are there, 3 or 4 or 5, I don't know. But, and I don't mind. Okay, so I'm just going to draw the supply diffusers. So if I place 1, 2, 3, and 4 here, and 1, 2, 3, and 4 there, those are the supply. Okay, of supply, and then we need return. Three and 4. And that will be a return diffuser. Get the same number of supply and the same number of return diffusers. Now, what is the CFM in each diffuser? We're in the gallery.
So it was 40,000. So we say 200 people. So it's 20. So it's 40,000. CFM total. For the room.
We have, okay, so this is the total people, but we had the total people in the art gallery. So in the art gallery, what did we say? I think here. Oh, so yeah, so it's 200 people in this space. So 200 people times 20, it's 2,000 CFM. Okay. If I have 8 diffusers,
2,000 on each side, because there'd be 100 people on each side.
Yeah, let's say, okay, so this is 2000 and 2000. So this is
250
250
each.
each. Yes, you're right. So that will be 250 CFM. We have 250 CFM for each supply diffuser. So I'm going to paint it blue and smaller. So this is 250 each. And are we sure of this? Okay, we have 200 people.
So that'd be 500 each.
So if it's 200 people, we have 100 people here, no, 100 people here, and 100 people there. So it's 100 times 20. This is 2000 CFM. If I have to divide this by 4, it's 500 CFM each. Does it make sense? It's 500. Okay, 500. For the supply, 500 for supply diffusers here, and then 500 for return, and 500 for return there. Okay, so that makes sense. So in Revit, we need 3, 4, 5 diffusers. I don't mind, okay, but you have to be consistent with the CFM and the number of diffusers and the total CFM that we have in that space. What about the lobby? So in the lobby, we have like 20 people maximum in the lobby times 20, it's 400. So if we have 400 people in the lobby, and 400, sorry, CFM, 400 people, 400 CFM. If I have 1, 2, 3, and 4, so it's 100 each for supply and return. Okay, so we can do the same here. If there is 1, 2, 3, and 4, and all these has to be 100. Hundred. In the other sections, we have different numbers, but I don't mind. Okay, we have 100 here, and now the return should be 100. Or can we have 2? Let's do something different. Can we have only 2 return diffusers here? We can. Okay, so all this flow goes here and there. That works, but now this is not 100. This would be 200 each. 200. And okay. Or I can have for return into supply, I don't mind. But the same supply flow has to be the same return. And now I have to connect things. Okay. So if I'm connecting things, it looks like there can be like two different branches. So I'm going to draw first the supply branch. It can be like this. This is one of the branches. This is another one. Okay. And now if I connect these two, there will be a shaft here. So from this one, we have to go up because the air handling unit will be placed on the roof because we have to connect this to the air handling unit. And now, what is the other one? If I connect the return, I can connect all these. And then I have to connect these two. And there will be another shaft there. So there will be an intersection here. I think in the other classroom or in the other section, we didn't have an intersection, so I don't remember what I did, but it looked nicer than this. Anyway, this lobby is very high, so having two different heights for the supply and the return, I don't think it will affect the thing. But that's okay. We can have something like this. Let me look at the in Google Maps. What is it? Okay, so this is the roof. We don't have anything on this flat roof here. But here in this flat roof that we have between these two gable roofs, there's some equipment. I don't know what this is exactly, but there's something here. Okay. That's good because we don't see, as you can see, all the buildings have something on the roof. Okay. We have the TDS building, and on the TDS building, those are the air handling units, those are the heat pumps, and those were the skylights thing. But all buildings have things on the roof. Okay. So we have equipment, probably heat pumps. Here we have solar collectors. I think there's like a chiller here. So all buildings have something on the flat roofs. Here we have air handling units, probably. This is the student center. Then for the dining, I'm sure that this is the air handling unit. We have heat pumps there and chillers there. So all buildings have equipment on the roof. In this one, it has equipment on the roof, but it's hidden somewhere. When we are here, we don't notice that there's okay. Okay, but I want to show you this. We can't get any closer. But if you look at this element here, we have this roof, this triangle, and if you walk there, this is open, okay? So it's not closed. It has like louvers. So I'm sure that there's something here. And this is a mechanical room on the second floor, and there will be some equipment.
So I sent you an email. There's plans and sections of the building.
But with the equipment, or
It doesn't, I don't have the mechanical, but it has like, it shows like over that space, it shows like there's a.
and there's a mechanical room there. Or is there-
Yeah, it's a huge mechanical room.
Okay. But I think there's something on the roof, because what would I do here? I think we need at least 2 air handling units because we need an air handling unit for this high occupancy area, and then we need another air handling unit for the low occupancy area. So we'll have both. Okay, I'm going to copy this slide here, and I'm going to get rid of all this. Okay. So this is for the diffusers and the ducts, and yeah, so I can assume that I have a mechanical room here on the 2nd floor. Okay. And now I have different options. On the other section, I assume that I have a boiler, and then I have what did I do? We have a boiler, a gas boiler for the heating, and then we have electric chillers for the cooling. Okay, if I place the air handling unit, the main air handling unit here, and I have the shafts for the return and the supply there, so I can have the supply in this direction. These are the supply air ducts, and then I can have the return air ducts here. And here we have the vertical one for return, the vertical one for supply. Okay. Now, if everything runs on electricity, I think I might need a chiller here, and that chiller needs to be connected to this the cooling coil of this air handling unit. And I might, if I have another thing here, then I can have this for the heating coil. That would be too expensive because I have two different. We have something for cooling, something for heating, and they are both feeding this air handling unit. Okay, and then I think I would use a different air handling unit in that mechanical room here. The same thing we saw in this building. So you know that for the office spaces, we have a heating the air handling unit there, and then if I place this air handling unit here, and if I throw all the air ducts in this direction, then I can have supply diffusers for all the spaces that I have here. Okay, and then I will need return diffusers for all the spaces there up to the air handling unit. So I will need the return users for all those spaces. And somehow I have to connect this to the heating coil. And I can connect this to the cooling coil. Okay. So here I have text. This is a chiller. And this is a heat pump. But only for heating. Okay. This is an option. I have two different heat pumps. One working only in cooling, the other one working only for heating. And why is that? Because at some point, especially when we have different spaces like this, we have an art gallery with 200 people, and here we have an office with only one person. This person can and might need heating, and we might need cooling for the main art gallery. So that's why if we connect everything to the same air handling unit and we connect everything to the same heat pump, when there are a lot of people in this in the art gallery, probably we will need, even if it's cold outside, but we will need some cooling because the people, we are releasing a lot of heat. And the poor guy in this office, if it's cold and this guy is alone in his office, or her, I don't know, and that person is receiving cold air because we need cold air in the main art gallery, so the system is not working well. Okay, so that's why dividing things makes sense. If we need cold air for the art gallery, I have the air handling unit connected to that chiller. And if I need warm air for this office, I have this air handling unit connecting to this heat pump for heating. So I think the system is flexible now. Can we do this in a different way? Yes, we can. But we run out of time. So if you want to find out how to do it in a different way, you have to watch the video for the other section.